Okay, so in this video we'll look at calculating K from initial and equilibrium concentrations. The entire process of these types of problems really comes down to organization, and that's what I'll focus on when we're doing this problem. I'll go through the math kind of quickly, but you can do that on your calculator. But mostly it's organizing and the way that you organize the data and the materials that you get. The second step is to use coefficients and do a little bit of stoichiometry. The third part is to subtract if you need to, and then you can calculate actual K for a particular reaction. So let's start backwards just a little bit, and then we'll look at sample exercise 15.8 right here, and we'll work it through step by step. First of all, you're going to find K. K, remember, is the equilibrium constant, and that's equal to products divided by reactants. And the products here in this sample question are hydrogen iodide, and we'd take the concentration of that and raise it to the second power because there's a 2, divided by the reactants, which would be H2 to the first power times I2 to the first power. Notice they're multiplied right there, not added, even though there's a plus sign right here in the chemical equation. So it's always products divided by reactants to the power of the coefficients. Now, we need to find what are called the equilibrium concentrations for these. Not the starting concentrations, but the equilibrium concentrations for these. And to be able to find those from a particular problem, lots of times you have to set up a table where you have the initial concentrations, the change in the concentrations, and the equilibrium concentrations. And that's where the subtracting comes in usually to find those. So let's go ahead and read the problem, and then you can write this down as I read the problem, and we'll set the entire thing up. It says, a closed system initially containing 1 times 10 to the negative third molar of hydrogen and 2 times 10 to the negative third molar iodine at 448 Celsius is allowed to reach equilibrium. At the equilibrium, the HI concentration is 1.87 times 10 to the negative third molar. Calculate K at 448 for the reaction taking place, and then it gives the reaction right here that I have written down right here. So step number 1 is to organize the data that we're given. So notice they use the word initially. So initially containing means that's the starting amount. And so it initially contains 1 times 10 to the negative third of H. So we'd write it down right here. 1 times 10 to the negative third. And it's going to be molar, so let's just omit that right now so we can fit it all in here. And I know there's more significant digits right there, but we're just going to write it down here so it fits in the table nicely. It initially also contains 2 times 10 to the negative third of the iodine right here. Now it doesn't tell us anything about HI, and so you have to make an assumption. They tell us about HI at equilibrium. See that word right there, equilibrium? But they don't tell us that there's any HI to start with, and so we have to make an assumption that there is 0 to start with. Now, sometimes they'll tell us there's an initial amount to start with, and then we have to pay attention and fill it in there. But if they don't tell us about it, then we just have to assume that there's none. It's allowed to reach equilibrium, and then the HI concentration at equilibrium now is 1.87 times 10 to the negative third. And so we look at equilibrium, and that's where we can fill in the HI as 1.87 times 10 to the negative third concentration. Okay, so that's organization. First, organize the ICE, sometimes called ICE table, initial change equilibrium values that they give you in the question. Now, once you've organized that, now you can go ahead and start to do some subtraction and using the coefficients to figure out how much of things were produced or how much stuff disappeared from one side to go to the other. So for this to go from 0 to 1.87 times 10 to the negative third, we must have added 1.87 times 10 to the negative third molar amount over here. That means we must have lost some of this and lost some of this, and so we put minus signs right here. And to figure out how much we lost, we have to use the coefficients for the reactants and the products. And so if we want to find out how much H2 was lost, we'd start with our I2, HI that we gained, 1.87 times 10 to the negative third, HI's, and putting HI in a position where it's going to cancel, and H2 as my new set of units. For every 2 HI's that appeared, 1 H2 disappeared. And now we could take this 1.87 times 10 to the negative third divided by 2, and we'd know how much of this disappeared. And they have the math right down here for us, and 0.935 times 10 to the negative third moles per liter, or molarity, disappeared, and this would go in for our hydrogen. 0.935 times 10 to the negative third. Now we'd do the same thing to go to iodine, and you'll notice right here that for iodine there's also a 1 in front of it, and there's a 2 in front of the HI, and so we're going to end up with the same number right here. So this is 0.935 times 10 to the negative third as well. So both that amounts were lost because it is a 2-to-1, 2-to-1 ratio. And now we can go ahead and do the subtraction. This minus this gives us our amount at equilibrium. This minus this gives us our amount at equilibrium. And the math is done for us right here. So you can try it on your calculator if you want, but in the end, H2 ends up being 0.065 times 10 to the negative third, and iodine ends up being 1.065 times 10 to the negative third. Notice this one was 2 times 10 to the negative third right here. Now, once we've organized, used our coefficients to find these out, done the subtraction, we now have the equilibrium amounts of hydrogen, iodine, and HI. Once we have these, we can put it into the K equation. So this goes in here for HI, this goes in here for I2, this goes in here for H2. Be careful, you have to square this one, and then these would be to the first power and these would be to the first power. And once you put those numbers into the equilibrium constant equation or equilibrium constant expression, when you push the buttons on a calculator, you should end up with 51 for K at that temperature. So, nice way to know it, just to summarize it again, make an ICE table, initial change equilibrium. Organize your data that you get. Put the initial pieces in. If they don't tell you about any of the products, assume there's 0. Find the equilibrium amount or amounts that they tell you. Calculate the amounts that are lost, or the amount that's gained, depending on what they give you, based on the coefficients, and then do the subtraction to figure out how much is left over here on the reactant side, or a plus sign over here for how much is gained on the product side. Plug them into the equilibrium constant expression, and bingo bango bongo, you win the Calculating the Ice Table prize.